Okay, so today's the first lesson we're going to look at is the language of proofs. So our learning intention is the knowledge in the formal language of proofs, and we'll be successful if we can understand what we mean by statement, proposition, or premise, an implication, the converse of a statement, the negation, and the contrapositive. Okay, so this topic, there's a lot of language, I would suggest looking at these videos a couple of times and actually reading your textbook to make sure that you have a better understanding or full understanding of these words. Okay. So, firstly, a mathematical proof is most often an argument that shows a statement or premise is true. Okay, so we've been doing quite a few proofs, and this is basically showing how in mathematics, we require proofs to identify certain mathematical statements. Okay, so there are 4 different types of proofs that we'll be looking in this course. Proof by induction you'll be looking at in extension 1. In extension 2 we'll be looking at a little bit harder ones. But we have these following proofs. So just to name a few. So inductive, obviously we have, it's where we observe one situation occurring. And if we can see it happening at another location, and its following sequence, then it should happen to all of them. All right. There are obviously steps. We have to prove the base case. We then need to make an assumption. We have to prove it occurs at the next step, and then we have to conclude. Okay. We have the deductive type of proof. This is where the statement is to be true so using known mathematical principles. It may require the use of algebra. And it has to be true for all cases. So some examples include n can represent a number. Yeah, that would happen for all of them. Something like n plus 1, or n plus 2 represents 3 consecutive numbers. Okay, so they're proofs by deduction. Contradiction. So proof by contradiction. This is where we assume the direct opposite of the statement. If we can prove that this assumption is wrong, then by contradiction, the proof, the statement must be correct. The original statement must be correct. Okay, so the steps for this would be assume the direct opposite. Need to prove that the assumption is wrong. State the contradiction. And then conclude. Okay. Counterexamples. Proof, a type of proof. So using a proof of counterexample. Counterexample is basically proving that for one situation, at least one situation, the statement doesn't occur or doesn't exist. Okay, so in this one we just need to find one case where it doesn't occur. Okay, so some things that we need to be aware. So a statement. A statement is a sentence that is either true or false, but it can't be both. Yeah, we can't have a statement that is true and false. It has to be either one or all. So for example, and usually when we make a mathematical statement, we give it a capital letter. So for example, I might use the capital P. Yeah, P for a premise. Yeah, or a proposition. So let's say n is a multiple of 3. Okay, I can give another one. So another example, that's a statement of Q. Even numbers are divisible by 2. We can do S. So for all real x values, the derivative of x squared is 2x. So they are all sentence statements. They're all they are true. Yeah. In this situation. An implication. So this is also known as a conditional statement or an if-then statement. So it's basically a two-part problem or two-part statement. Usually P and Q stand for separate parts. So for example, I'll make a statement of P, let n be a number. So n is a multiple of 10. And let my other statement Q, n is an even number. Okay, so I can state P implies Q. Yeah, so if P is a multiple of 10, so we've got 10, 20, 30, multiple of 10, 10, 20, 30, 40, 50, 60, yeah, it implies that it's also an even number, which is true, yeah, so 10 divided by 2 is 5, 20 divided by 2 is 10, 30 divided by 2 is 15, so that is true. So P, and we read this as P implies Q. Okay, or we can write, if P is true, then Q, or if P, then Q. Okay. The converse is the reverse of the implication. Yeah. So the reverse would be if P then Q, so this is the implication, then the reverse is if Q then P. So this is the converse. Yeah, so okay. The converse may not be true. So if you have the first implication, it doesn't necessarily imply that the converse is also true. So the converse may not be true. And if we took our example, yeah, so if I have a number, which is a multiple of 10, it implies it's an even number. But if I took its converse, if it's an even number, it doesn't necessarily mean it's a multiple of 10, because even numbers include like 2, 4, 6, 8. So 2, 4, 6, 8, they're all even numbers, but they're definitely not multiples of 10. So the converse may not be true. Okay. Our next statement, equivalence. So if the statement and its converse are both true, then we take them to be equivalent. Yeah. So the term if and only if, which is also represented by the acronym or shortened by IFF, if, is used to describe equivalence, and so is it simple. So, for example, if we have, let's say one statement is x is equal to 5, and my other statement is 2x equals 10. Well, if it's P implies Q, that's true, and Q also implies P. So therefore, P and its converse are equivalent. Yeah. So P if Q, yeah, or we can write P if and only if Q. Okay, so if we have the statement and its converse are both true, then they are equivalent. Negation. So negation is the statement of P. So the negation of a statement P is to say not P. Okay, and we can use these symbols. So that sideways LP or P dash or tilde P or P line. Yeah. So if P is true, then its negation is false. And if P is false, then the negation is true. When statements are in words, be very careful about the negations. So some examples of negation. Let's say I have a proposition or statement that I say the number is even. Yeah, so its negation is the number is false. The number is odd, or the number is not even. Yeah, so therefore it'll be false. do a question, so it's a statement that fish swim in the ocean. I can't write the negation fish don't swim in the ocean because that would not make any sense. But I could say not all fish swim in the ocean. Okay. Contrapositive. So if we have a statement that P implies Q, then the contrapositive is not Q implies not P. So let's do as an example. Let's say P was n is a multiple of 10. Q n is an even number. Okay, so definitely P implies Q. So we have it's multiple of 10. It also implies that that has to be an even number. So if we do the contrapositive of Q, so so if we're going to do the negation of Q, the negation of n is an even number, is n is an odd number. Okay, and the negation of P, so n is a multiple of 10, is n is not a multiple of 10. All right, and if we believe, so the negation of Q implies the negation of P. So if n is an odd number, yeah, it implies that it's also not a multiple of 10, which would be true. Okay, so these two, the contrapositive, and its equivalents are kind of the same. So if P implies Q is true, then the contrapositive of negated Q implies negated P is also true, and vice versa. So if P implies Q is false, then the contrapositive of the negation of Q implies negation of P is also false. Okay, so P implies Q and its contrapositive are equivalent. Okay, they're the same statements. Some symbols that we need to understand and get used to seeing is quantifiers. So this upside down A, that means for all. Okay, we can use a statement. So for all of X, that would look like X values. I can do that. Backward E stands for there exists. There exists a value for X. Yeah. Some understanding of numbers. So these double letters, so these double fancy letters. Okay, so if you see the capital N, yeah, that stands for natural numbers. And these are counting numbers, things that we can count. Yeah, so 1, 2, 3, 4. Yeah, things that we can count. Z, set of integers. Okay, so these are whole numbers. Q, a set of rational numbers, so these are all numbers that can be represented as a fraction. So real numbers, they belong to all of these numbers. Yeah, so they include natural, integers, rational and irrational numbers. And complex numbers we haven't seen yet, but they are in the form A plus BI, where A and B are real numbers. And I is the solution of x squared minus 1. And we call that an imaginary number. Okay. Some other symbols that you would see is E, or this rounded E. Yep, that means is an element of or belongs to. 2 column means such that. I'm actually going to put some other ones. So we've got where it's a sideways U, that means a subset. You've already seen that for the union and that for the intersection. Okay, so there's some more symbols. Okay, and that's it for this lesson. All right. So today was just basically getting some idea of some of the language. And as I said, it's a very heavy content. It does take a while to get an understanding of this. Go over your notes, read them, watch this video a couple of times. It's just getting an understanding of the different types of proofs and the different types of languages that we use in proofing. Okay, thank you.